everybody. Good afternoon. I am Jeanette Gonçalves. I work for WavEC at the communication department, and we are going to start this webinar. First, we have here an introduction, and we will wait for more people to join. Thank you all for attending this webinar on high-performance computational modeling and data science capabilities for a renewable blue ocean. The presentation will last about 45 minutes, and then we will have 15 minutes time to reply to some questions. You are all muted, so if you have a question, please write it on the platform, and then the speaker, Guilherme Vaz, is happy to answer as many questions as possible at the end of the session. So an introduction of Guilherme. He is the head of HPC and Data Science Team at WavEC. He is an aerospace engineer with PhD in Mechanical Naval Engineering at Instituto Superior Técnico, Portugal, and at Maritime Research Institute of the Netherlands. He is an expert on computational potential and viscous flow tools and high-performance computing. He has 20 years of experience on CFD, hydrodynamics and aerodynamics modeling of maritime, ocean engineering, and renewable energy structures, and has published more than 125 articles on these topics. So, Guilherme, I would say the floor is yours.
So, thank you, Jeanette. Are you hearing me?
I am.
Can you see me?
I can see you. I will switch off my webcam. I see your presentation.
Okay.
So if any attendee has a question, please raise the question and I am happy to help, or Guilherme at the end of the session. Thank you.
So thank you, Jeanette. So thank you, everybody. So this is also my first time in a webinar of these magnitudes, and the first webinar at WavEC, like Jeanette is saying. As you can see, I'm not at WavEC. You can see from behind, due to this pandemic, I'm working at home, and believe it or not, it's raining a lot in Portugal. So it's a perfect timing to do a webinar here, and I hope I can entertain you for the coming 45 minutes. That, knowing myself, and some of you know me, it will not be 45, it will be 50, but I hope I can answer some of the questions that you have. If you have any technical problems, please ask Jeanette, because we cannot see what you are seeing. So today, of course, it's going to be some talk on what I have been doing in the last year here at WavEC. So Jeanette didn't say, I was working last year. I came from Holland. I was 18 years in Holland, and this 1 year I had to adapt myself to the reality of Portugal, to the reality of WavEC, and a lot of learning. So, and me, my team, and a lot of expertise, and a lot of other people helped me to in the last year to do different things, and I'm going to tell you about these things. So, so the overview, the presentation will be on recent developments, HPC, CFD, and new stuff I had to learn, and I'm very pleased to have learned, because it's a very motivating field. It's data science. So I will give you an overview also of WavEC capabilities in these domains, and some applications to show a little bit what we are doing on these fronts, can help you to know what we are doing, but also new ideas for you, and for cooperation purpose, for services, for projects, whatever. We're going to show you a little bit what we are thinking, and I finish with some trends and plans. Disclaimer. One cannot be expert in all these issues, in all these topics. So a lot of these things I learn, or I see, or I have done together with other people. So I acknowledge all the work, discussions, and ideas and knowledge I gain by working with in the University of Duisburg, Essen, with whom I'm still affiliated, with Maren, that is in my heart, IST, that is my university, Southampton, when I'm visiting researcher. The Ocean Cleanup, that is, you will see, it's a company and a startup with whom we work a lot, and WavEC, of course, specialists, and a lot of students. So I do like to work with students. So let's go. For the ones that do not know WavEC, WavEC was started as being a wave energy center, the name WavEC, but now we do much more than that. We do everything related with offshore renewables, and that's why we now WavEC Offshore Renewables. It's 17 years ago. It's an association, so non-profits. It's multidisciplinary. We have now currently 4 big teams, and I'm just going to show something about my team. That's the HPC Data Science, and not about the other 3 teams. So this is just 1/4, let's say, of the activities that happened in last year at WavEC, and so I cannot speak for WavEC in a whole, but mostly on HPC and data science today. We are around 30, but we have a lot of PhDs and master students, and we are close connected with the universities, and with the we are also a small research institute association. So we have a tendency, being a research-minded company, to do a lot of partnerships. So that's a little bit about WavEC. It's in Lisbon, in Portugal, and now we come to our topic. So when I came to WavEC, and even already last year in the Netherlands, we already spoke about something that people were speaking about, the Industrial Revolution. Well, we know about the Industrial Revolution, the first one, the second one. We know about the first one, the water and the steam and the engine. The second one, people speak about the electrical power, electrification of everything. The third one of the electronics, and now people speak about the fourth Industrial Revolution. And that's the age of automation and data exchange, or the digitalization. That's a way of seeing it, the fourth Industrial Revolution, and or very, very, very rarely, very scarce, and it was very expensive. So that has changed, and now we have like 3 big companies, or 3 big institutions, like European Union, but in America also NASA and NOAA, where they have a lot of public open source data. Well, like it or not, one of the guys that has pushed the open source in all kinds of sense was Google. And you see Google like being one of the catalyzers for data science and data. And you know all Google Maps, you all know Google Earth already 10 years ago, and that was one of the first initiatives that really pushed a lot usage of open source data and satellite data, even if Google Maps is a lot of airplanes. But and you can see this was supposed to be, so this is WavEC here in Lisbon, and if you zoom in a little bit, this is still WavEC, where we are close to the marina, and it's not today, because today it's raining like hell. So apart from HPC and big data, we have artificial intelligence, and that's something that people thought some years ago that it's like science fiction, and it started already a long time ago. I'm not going to say all the details here, but 1943 already people spoke about artificial neurons, and then there was also computers done only to mimic the artificial neurons in 1956, and also in the first very famous conference, people start to speak about artificial intelligence, for neural networks. But then for 20 years, this faded away a little bit because the computers were too slow, and there was not computational power and memory enough to store all these things. And then in the 90s, with the boom of the computers, they started again artificial intelligence. I think everybody knows the Deep Blue and the Deeper Blue computer that was playing chess against Kasparov, and that's one of the first examples of artificial intelligence. And in 2000, I have to say, it appeared very similar to the rise of Google and this type of companies. We have a boom in machine learning, and then also in deep learning afterwards. Mainly 2 companies that everybody uses. Sometimes we say a lot of less than positive things about these companies, but they were really the like I call it, the catalyzers of these technologies and of making everything open source for everybody to use it. So neural networks had a long time ago, machine learning in the 80s, and now we are talking about deep learning, so machine learning combined with high performance computing. What do we do at WavEC with these things? So one of the things, and it's the core of my heart, like Janet said, we have some expertise on high performance computing. So we have a mini cluster at WavEC. It's not big, it's mini, but it's good for the size of the team we have. Well, I always want more, of course. But we have access to some of the biggest clusters in Europe and in Portugal. So it is in UK, Magnitude in Germany, Bob in Portugal, and Navigator. We have had access for testing, and now we are trying to get access for more research. And Marcus 4, because we have a cooperation with Maren, and Maren is very kind to let us to do some research on that cluster in a joint project. So you can see that in total, we have around access to 50 or 60,000 cores, nothing to do with Fukaku, but it's still a lot of cores, a lot of computers that we can use to do both computational modeling and artificial intelligence. Why you need these computers? I mean, our computer is not fast enough. Now, we are talking about things that really need a lot of computational power. You will see afterwards both high fidelity numerical modeling and artificial intelligence for training the models. Because of the quantity of data they are needed to get accurate, we need these kind of technologies. So without these technologies, without the push also for the opening of these technologies, it will be very difficult to advance in the other two. So at WavEC, we have this thing in this computational modeling that fits in the HPC, two types of tools. So what we call the engineering tools, so the medium fidelity tools and the high fidelity tools, or the viscous tools or the CFD tools, the computational fluid dynamic. For the medium fidelity tools, we use a lot of tools that a lot of the engineering world uses, like WAMIC, OrcaFlex, FAST from NREL, with whom we work sometimes. We have our own in-house time domain tools. For instance, here an example, if you can see the movie, it's an example of OrcaFlex and simulation of some open water tests of cages, of aquaculture cages, where you can see also the moorings. And this was a complex simulation for OrcaFlex. But so this is like a simulation tool that is fast. And it's not that we cannot use HPC. It's fast in a normal computer, but if you use HPC, it's even faster, meaning that we can do optimization. And we can use these tools, these medium fidelity tools, for something that was speaking last slide, that is the digital twins. So we need fast tools that can learn with artificial intelligence in order to make it to be fast enough to predict what's happening in the real world. So these medium fidelity tools are not going to disappear. They are needed. So we use also OceanWave 3D, now starting to work even more with that open source tool. We use noise propagation tools, and we are very fond and very believers on open source. So we have also our own GitHub site where you can see in this link here which kind of tools we make open, which kind of tools from the others we use, and we adapt and we give it back to the community. So, and this is we just started 1 month ago, and this is growing very fast because we believe in this. Now, for the high fidelity tools, we speak about viscous flow, CFD, computational fluid dynamics, and I have to say that the experience we had with Maren, and WavEC already had worked with Maren for a lot of years before I came. And I was one of the founding fathers of a code that belongs to Maren, there's Refresco, and we develop together with Maren and other companies. And the same side, we are also representing a commercial code. So this is more community-based, open source code, community-based that Maren controls code, and this is a commercial code. And what you see here, some typical examples of applications of CFD for a ventilating propeller, for a buoy, and for a submarine. And so we use at WavEC both Refresco in cooperation with Maren and others, and FireMarine in cooperation with Numeka. So these are the high fidelity tools that do need HPC. Now, what about big data? Now, you saw that we started in 2003, so we have like 17 years of data. Fortunately, not all data is gone. And there are backups for that, because 17 years of data is a lot of data. And only now, let's say only in the last year now, we can really try to automatically analyze all the data that we have been gathering in these 17 years. So I can imagine institutions that are already here for 100 years, they have much more data even to make something out of this fourth industrial revolution. But at WavEC, for instance, we have buoys that were sending data from I think this is close to the coast of Sesimbra, that was sending data to via internet, via 3G. We're sending data to WavEC, and we can analyze both the velocity, temperature, salinity, and noise. With the hydrophones, we have also a ROV where we can go and get a lot of data, and with the ROV, we can get it automatically at the moment, and we can also have videos, and we would like to use also artificial intelligence to analyze those videos. So we have done several field campaigns, full-scale noise monitorings. We are working on ACT, so it's a kind of platform where there's two pieces of sea, two pilots locations in the sea, in Augusta Doura and in Viana, in north of Portugal, where we can also do monitoring and campaigns for sustainable solutions and for renewable energy. You can see more on our site, and satellites. So there's a lot of initiatives on satellites, and we are working on trying to use satellite data, open source satellite data, and commercial one with better resolution for our purpose. In terms of databases, we have like an European biofouling database that is like unique. So where all the natural and non-natural species, I forgot now the name of this non-native species around these coasts. And biofouling is an important thing, especially for devices that are not moving a lot, but even for ships, they're also important. There's databases with 300 ports where we can have all the data, and we have 16,000 full characterized vessels in a database together with other partners. So all this data is here to be analyzed and to be used and to do something with that. So on the data science, on the artificial intelligence side, we are learning, like I said. But thanks to the Googles and the open source and to the Python community, we are learning quite fast. I mean, all students now coming from the university, they know a little bit about that. So we started with MSc students from IST, and we started with the machine learning and deep learning approaches. And we started somewhere. We started with an example like this that I will show you afterwards, that is to analyze images to quantify visibility. And of course, we use a lot of these open source libraries, and this is very much in cooperation with the Instituto Superior Técnico, so this biggest engineering university in Portugal. So as a summary of some activities that we do in order to give you some examples, so on the side, on this triangle, I didn't put the big data, otherwise it will not fit here, but on the side of the artificial intelligence and on the side of the computational modeling or the high performance computing, so we have done things, and we do things, it's our core business, on wave energy, on tidal, on offshore wind, on aquaculture, on noise, acoustic sources and noise propagation is not the same, waves, ocean cleaning, and decarbonization. Of course, this is also very in our core, being WavEC, a renewable energy based company. On artificial intelligence, learning not only the models, as you see, it's a term that we use, but also we are learning. And we have done things on underwater detection of objects underwater with images and sounds, automatic detection of biofouling. We will like to work on that, and underwater species also. We are using now something from Microsoft to do some underwater species detection. And also we would like to do something on plastic tracking using satellites, imagery and satellites, all other kinds of satellites. So these links both together with the data that we need for this, and this in bold is some examples that I would like to give a glimpse of the examples for you to have an idea what can we do now with this in these fields. I chose only some. So one of the examples, this was done together with Maren. It's not here the link. So this is research work together with Duisburg University and Maren, and it's on floating offshore wind turbines. So a floating offshore wind turbine, it's turbines that are operating in deeper waters. So for instance, in the case of Portugal, where our coast is deep, not the case of the Northern Europe normally, or the North Sea, where more fixed, but here in our coast, more floating. And we all know now these three principal power concepts that are already in Viana do Castelo, and are similar concepts as this one. So a semi-submersible concept. So it's a turbine mounted in a semi-submersible that is moored to the ground, to the soil. And there's a lot of topics that has to be taken care of. And you can take all these separate topics, and you can do some work on these in order to improve your tools and verify and validate your tools. But afterwards, one of the things we believe is that the design of these of these structures has to be done in a holistic approach, so coupling everything. We still didn't arrive there, but we have the tools to do it, and it's like step by step we're arriving there. So in this study, together with Maren and Duisburg, what we have done, we have tackled one by one topic, not the blue one still, but we have tackled the aerodynamics a long time ago. Then in respect with the winds, so we have tackled the waves, we tackled the currents, we tackled the wave loads on the structure. And in this presentation, I will show you some example of the rigid body motions and mooring effects on the modeling of some of platform using high fidelity tools. So, and one of the things important is the hydrodynamic damping. Aerodynamic damping is important for safety and efficiency. You don't want the structure to be excited by waves and currents and just collapse. So we want to analyze the damping, and the damping is not only good to be analyzed in terms of high fidelity, but also to get more experience and to get more grasp on how the physics look like, but also to get values that can be used on low fidelity tools or can be used in digital twins, because these tools are quite expensive. So that's why we have done here, verifying, validating solutions of high fidelity codes for all these topics. So this is an example we have done. So this is the NREL OC5 concept, and this is the structure, underwater structure, how it is. The turbine is there in terms of mass, inertial, and structural properties, but it's still not working. It was not the way that was done. It was not operating. It's not the day that the experiments were done. Experiments done at Mare and calculations done at Duisburg and together with WavEC. So this is an aspect of the grids and of the geometry itself. And this is an example what could do. This is a real simulation of a CFD, in this case with the Refresco code of floating offshore wind turbine moving in 3 degrees of freedom, where you do a decay test. So you push the structure and you leave it and you see when it decays. And when it decays, you can compute afterwards the natural period and you compute the damping. And that's those things that are important for the numerical behavior, the hydrodynamic behavior of the structure. So you can see the free surface with some colors on the velocity, and you can really see the surge, the heave, and the pitch motion. Watch out with the scales of the real structure. And we can do this in model scale, and we can do this in full scale, and we can do this with waves. And there's already work done with waves, but I didn't present it here, together, for instance, with Texas A&M, another university with whom we cooperate. So this is just to give an idea how the flow looks like. And astonishing or not, small difference on the flow, small details on the structure, small details of the moorings have a tremendous impact on the damping. And that was something that it's really like, that's something that really like for us eye-opener. So you can really see here like some numerical experiments, some calculations in the left done with some settings and some numerical and physical settings, and the right the full what I call singing and dancing stuff with all the moorings and all the aspects, and with turbulence modeling and with the free surface correctly model. And you really see them small difference in the flow details and on the damping plates. These are called damping plates. They are done there. They are there to make some damping. And this small difference, they can have damping effects of 2%, but the damping effects of 2% are quite, these are quite sensible. It's we have to be careful with this difference. So it's a nice way to analyze the flow that is very difficult to do in experiments, being a model scale or full scale, and you cannot do any other way than with these high fidelity tools. Really analyze the effect of putting a pipe in this structure or a heaving plate, and what's the effect of that on the damping or the behavior of the structure. So for instance, here is an example what we would like to know. So the difference between the difference between in time of these two peaks is the natural period, and this is something related with the damping. And we could really wanted to compare with experimental results, and for that, moorings were the problem. If you don't model the moorings correctly, like the moorings that are in real life on the experiments, the results are different. Let's say if you compare the red one the red line with the black part, you really see a big difference both in period and in damping coefficient. We also are very careful. That's something that we learned from. I learned also from my previous supervisor at IST. We are very careful on a numerical result. So we try always to verify and validate our results doing a certainty analysis. So we give a result, we try to give a result with an error bar in colloquial language. And you can see that, for instance, here the experiments, we don't have error bars as supposed to be, but we have an error bar for the computations. So we try to push a little bit the experimental guys to do also this analysis in order to say you cannot do anymore just the computation. You say the computation is good enough, and for that you have to assess if this is good enough. That's also a good thing from artificial intelligence. You get the result always with an uncertainty, also always with an accuracy. And in CFD or in engineering tools, we should do the same as well as in experiments. So in this case was the mooring, the characterization of the mooring, of how the mooring was done in experiments was very difficult, and we had to do a lot of trial and error in order to model correct the moorings. And when we have done that, all the other aerodynamic specs were captured well, and then we were really very close to the experimental data. But it was a very difficult burst of some years in order to verify, validate all the different experts and to get this correct. So, but now we can do it, and we are already doing for another turbine, and we are doing now together with Delft and with the University of Tokyo. And you can see in our GitHub some open source data will be there on the experiments, but also the numerical results, both with Refresco, Fine Marine, and OpenFOAM. We will do the same and the experiments from Tokyo, and we will do based on this on these lessons learned. We will try to also do the turbine and see if we get good results. Another thing it's also important for us, environmental impacts, and something that is the public opinion is now being very careful about is noise. And not only noise, we're talking about underwater noise. Underwater noise can be important for defense applications, but underwater noise really disturbs the wildlife and the cetaceans, so that the whales and the dolphins, but even the fish. And there will be strict rules for harbors and for ships regarding noise. And so one of the topics for the decarbonization is not decarbonization, is more like denoisation. It's like making quiet, making stealth. It's how to control the noise, how to control not only the noise sources, but the noise propagation, and if we can do something out of that. So together also with the partners that have experience on that, in this case, TU Delft also included in the normal crime partners that we have here together with WavEC. We have PhD students and we have workers working on all kinds of problems with noise. So noise source modeling can come from in the water from moving objects, like imagine a propeller or an engine, but I'm talking about either dynamic noise, from the turbulence, but also from cavitation and from ventilation. So in order to identify the noise sources, we are studying those things, and together with PhD. So this is an example, already some old work that I had done when I was at Marin, where you really see a ship, and you see a propeller, and you see the noise generated, and even the pressure fluctuations on a ship due to cavitation on a propeller. So propeller, rotation, and cavitation. So also the rotation creates noise, but also the cavitation. And these two things are one typical example of noise source. Another example of noise source is boundary layer turbulence. It's more difficult to tackle. It's higher frequency, so sometimes more broadband, so tonal, and this is more difficult because it needs a level of accuracy even higher than normal CFD, and so HPC is really needed, and that's something that especially Marin is working on that, and with TU Delft and the PhD together, we are working on that also. But that's just to identify the sources, and once you have the source, where the noise goes and how does the noise propagate. And if you have a mountain or a rock or the bathymetry, and if you have a coast, and if it's the noise at 10 kilometers or 20 kilometers, how can you map that? So how can you make a noise map based on a source? And the source, we can go to the field and measure the source, as we had done before. And now we can also compute the source. So we can also now try to see by experiments or by the noise computed, where does the noise propagate? And we are checking this a lot of it's classical tools that were done a long time ago, and we're trying to improve them, like IT-wise, parallelization, new techniques of making them faster. They were already fast, but if you want to use them, for instance, for digital twin, we have to make them even faster. And we compared those tools with more elaborated tools, also like a tool of commercial code, and try to see what are the benefits, the pros and the cons. So what we want to do is that, imagine this is an example of noise map. It's a typical benchmark where there's available data of close to Korea coast. I don't know where, but now I don't know the details. But imagine that we have the 6 sources. This is the bathymetry. So negative here is it's above the water, and this is the really depth. And you see all the sources. The sources of specific amplitude and frequency. And we would like to make a noise map on this location. And so what we are doing with this specific noise propagation tools that, for instance, are known, like Bellhop, Kraken, and RAM, already from the 90s. And we're improving those tools, and we are doing these noise maps to at the end to do noise maps of ships and of any kind of structure, and measuring that or computing, or even afterwards to identify by using artificial intelligence. And we'll see, but our goal is to do noise maps in any part of the coast of anywhere using these tools, and to really use the best out of these tools in order to compute what is the noise amplitude at a specific location based on some noise source at other specific location. So we are going here. We have some students working there, so it's nice to see. And there's already even noise maps from shipping, from the noise of all shipping done, but it's a database and it's static. We would like to do this on the moment and when we want, and for a specific location with much more precision. My third example of HPC, it's something that it's really fun, and it's really like I think very actual, because you have seen it even in all news in Portugal, but other places. It's ocean cleaning. So we have been working, and me personally, I've been working together with ocean cleanup already since 2015. They have a lot of good friends there, and it's a small world. And we started to work together on the modeling of their devices. So what the ocean cleanup wanted is to clean the plastics out of offshore. That's where they started. But they've been seeing this graph where the plastic comes offshore. Most of it comes from rivers and comes from onshore. They're also now trying to clean the plastic in the rivers, and they have like the concept they call the interceptor. And they also have a device. There was system 1, they call it Wilson, and they were deploying it in the Pacific area, where you see there is a big patch of plastic, big great plastic patch, where in terms of area, it's almost like you see here in this gift by Ocean Cleanup, that is the size of 3 times the size of France. So that's the plastic that arrived offshore, and that it accumulates and it's just floating. But as a lot of other plastic does not arrive there. So what we have done, we have worked a lot with ocean cleanup. But one of the things that's that we have done together, really together in open source, is the development of a plastic model, so plastic drifting model, and we can model the plastic and the plastic wall interaction, because at the end we don't want only to help them, or the ocean cleanup doesn't want only to design a system that can survive, of course, but also design a system that is efficient to capture the plastics. And that's why I'm going to show you, because it's also an open initiative between us two. So this is the Wilson. So the system they had deployed, these are public pictures from kindly provided by the ocean cleanup. And so this is a system that uses the current in order to form a U shape, and uses the difference of velocity between the plastic and the current, because the plastic does not go, it's not a particle that goes with the current, because it has mass, it has inertia, so it has properties, and uses the difference of the velocity, that drifting velocity, in order to capture the plastic in the screen. And then somebody afterwards had to capture the plastic. So this is a sketch of an example of the floater, of the retention area, and of the system 001 Wilson in the Pacific. And here are some plastic, some pictures. And so what did we help them, or what did we do together, in fact? So there were also experiments done, and there were also computations. So we were trying, for instance, different moorings, for instance, more on the top, or moorings more in the bottom, and see what's the behavior of the system, for instance, for different currents, and comparing experiments with numerical models, and also under waves. So this is all only under currents, and this is a comparison. There's no verification done here yet, and we have a master student, so hopefully we'll start to do that. And this is the behavior of the structure in waves, and so the comparison of the experiments with some preliminary computations. And this was like preliminary studies, but we advanced more because we really had to push on the numerical modeling of the plastics. And so this, for instance, if you have some plastics that they have lower density, they're going to float, they're going to the surface. These were just tennis balls, or kind of, and to see the drifting due to the waves. And afterwards, having a piece of the Wilson system, really modeling. And this was a calculation that was done by a colleague of mine at Marin some years ago, and kindly allowed me to show here. And this was done together with ocean cleanup. And so this is the piece of the ocean, the piece of the Wilson. And then at the end, what we would like to do when we push a little bit more advanced, what is this, is to see if you drop some plastic here. Don't ask me why is this ball there. It's lost. It's something in the movie. And if you have some plastics with different properties, what happens with the plastic? And if the plastics go above, the plastics go below. So that's what we are studying now. And yeah, it's going. We are almost there. We can do plastic. We can do the structure. And we are now working on the plastic structure interaction together with the ocean cleanup. So that's ocean cleaning, where it's still an ongoing project, and it's a nice project to work, also to do something for our coast. And that was the HPC side, and now some interesting stuff on artificial intelligence before wrapping up. So also again, noise. And what we'd like to see, what we'd like to do is, like, we're measuring noise. We go with our buoy, we go with our hydrophones, and we want to automatically at the moment, or anybody's or measuring and sends the data to WavEC, and we would like to see which kind of animal, which kind of object, which kind of fish it's underwater, just based by the sounds, and just using sounds. And for that, we had some data already from our campaigns. We had open source, and we were studying, and so we used some technique that in fact uses image processing to do image processing. A typical artificial intelligence is used for image processing, like CNNs, convolutional neural networks, to analyze images, to analyze this topic. So I'm not going to speak about the details about the CNNs, but if you type in Google CNN artificial intelligence, you get a lot of hits, because it's really very it's a hit now. But this is like using trained CNNs to define underwater objects based on sounds. And so what we do, and here I have to do a trick, because this webinar does not work with sound, but I hope you can hear. So on the left, so we have the sound. It's the sound of a whale. I hope you can hear.
I cannot hear it.
No, okay. So, but if you cannot hear, then this is the sound on the left. I have the sound of a whale on the left. So, and then from the sound of the wave, so we pass to a spectrogram, and from a spectrogram we have a picture. And this on the right, we have the sound of a ship, and this is the sound how it works with the ship. And from the ship, we pass also for a spectrogram, and we have also a picture. And on the right, we have just noise. simple noise from the sea, and we pass from a picture. And from these pictures, we can analyze using normal artificial intelligence used to recognize animals or recognize anything that Google done for identifying images in order to say which kind of underwater vehicle or animal we have. And that's what we have here. Then this is again a signal where it's now not only the signals that we have used to train, but it's a real signal, and we want to identify which kind of animals or which kind of objects are here. And this is just a part of the signal. This is the complete signal. What we would like to do, and this is possible, is that when we are hearing the sound automatically, we don't have to do all this work of training. And I'll go to next application a little bit more into the training. We don't want to do all this kind of training, but we want just when we are analyzing the sound, automatically the signal saying we have a whale, this is noise, we have a whale, and this is noise. So I'm still working on this, but very shortly already now we can just by the hydrophone. Now still as a post-processing, we still have to get the data, but we would like to have this at the same moment that we are listening to the sound to identify which object it is, just pure by sound, not by using cameras. So that's one of the examples. The other one, like I said, is the visibility. So we would like to see in a port based on cameras. Now in port, normally the visibility, or you can do it in different ways, or with very complex numerical models for weather forecasting, or with some devices called visible emitters. I don't know if the translation in English is correct, but they're quite expensive and they can be only in one place. So if we deploy several cameras, if we can use the artificial intelligence and these several cameras to quantify what's the visibility in order to tell to the operators of the harbor if it's safe to enter in the harbor, or for the ships, to ship owners or the ship captain to see if it's safe to enter a harbor. And I say the harbor, but can be any place. So what we need for this, and this I'll go a little bit more in detail on how we need to do this. So we need data. So we need, in this case, pictures, and we need labels. We need to have a picture that says this is visibility of, I don't know, 500 meters. This is visibility of 200. This is of 5, and this is of 1. So you need the data, and we need labels. Now afterwards, we need to pre-process the data, because some of the data sometimes is not good, or it's not in a nice format, on the good resolution, or we have to do some processing on the data. Then we put this on this artificial neural network, so CNNs, for instance, or any other, in this case, other. And this is which model we should use. And there's a lot of work done on that. So we need to know which model we should use. Then we need to train the model. We need to have a lot of data to put in this neural network to iterate and train a model. Once we have the model trained, then it's very fast to see when we get one picture, if it's visible or not, and what's the visibility. The training to construct takes a long time and it's HPC, but not for testing. And that's why for testing, we would like to deploy this real life in hardware close to the harbor. So how does this work? For instance, this is images. For instance, this is Manhattan, and this is the original image, and this is an image with fog. And we have to do 3 filters. We have the original one and 2 filters, this high pass filter and some kind of called spectral filter. And by using not only the original image, but these 2 images, we have a neural network that's a little bit more complicated than a usual CNN. And this was based on a lot of research, state of the art. It was not done by us. We have to study what other people have done. And we can train a neural network that it can tell us afterwards if we have what's the visibility or not. But for that, we needed data. So we went to use a database that is funny because it's database computer-based, computer-made, so the computer-generated images of fog. So it's a street and signs and with fog. So this is still not a harbor, but it's something that we use to verify our network. And so how does it work? We have the original, we have the 3, we put in our VisNet, visibility neural network. And at the end, based on its image, we want to know what's the probability of having these visibility ranges. And in this case, this is 400 meters, say 0 for the other one. So that's what we are doing, putting the image, having the data, and getting the visibility. So does it work? Yes, we have used these 3,528 images to train, and we get an accuracy of very 95, 96%. And one of the things we have done also is that to train only with these images, it takes a long time, and it took us more than 10 hours in one normal computer. So we tried to use HPC in order to train this data with only 3,528 images, and it scales not linear, but it scales well with CPU time by parallelizing the networks. And you can see that if you use 20 cores or 20 computers, 20 cores, you can go to a training time of 3-point-something hours instead of 11 hours. So HPC will use tremendously because we didn't put this still in a big cluster, but we'll do, and we can train this in much less time than this. Of course, this will have a limit, but that's for training. After being trained, once we have this model, we can test one image in 0.5 seconds in one core. So to train, you need HPC, but for testing, we can deploy it anywhere, even in a mobile phone. And that's the power of artificial intelligence for these applications. So for real data, we have a problem. How do you get real data for hardware? So we're doing, and it's the technique everybody's doing, is called web scraping. So go to the internet, we get images, we get also the visibility by a website, and we get all the images via internet. We are downloading automatically image from the internet, getting in our systems at WavEC and running the train network. So we started this some months ago, and there's not a lot of folks still in Manhattan or in San Francisco, but when we're getting now some images of fog, once we have images we are going to train, but we'll get much more than 3,000, and so it will take some time to train. But that's what we are doing with visibility. So soon we can deploy something for, I don't know, for anywhere where we can have the cameras installed. So to finish, some trends and some conclusions. So of course, there's a lot of trends that we cannot say in one slide, but on HPC side, there is always the balance between using own computers, going to cloud solutions, or going to high performance computing. And I have done this several times. And when you do use a lot of HPC power every day, like we are doing at WavEC, cloud solutions are still too expensive, really factors of magnitude. And so we prefer HPC, and there are a lot of HPC centers for research purpose, very affordable. And thanks to the government of the European Union, but also for American government, they're pushing a lot on this, and for the universities that then allow us to work on that for research purpose. And now there's an internal fight between Intel and NVIDIA, and now NVIDIA just bought ARM. So ARM is the technology for making processors that is not based on Intel, and just bought it. So you will see a lot of movement in HPC that I cannot predict. On the big data, the big thing is the satellites. The democratization of satellites, or on types of satellites, so SatNav, satellite navigation, SATCOM, satellite communication, or SATEO, satellite Earth observation, or 5G and 4G. These are all things that are coming, and institutions are opening more and more the data, and but the data still has not very fine resolution. So we would like to have more worldwide initiatives, and there are going to be where they have further democratization of finer resolutions. And so we will work on that, and you will see in the next slide, we are working already with satellite data for some applications. On the data science, it's a world. It's a lot of research going on, papers going that. People use it as black box. It's kind of dangerous approach, but one of these applications we use it, another one not. There's also the link between numerical methods and artificial intelligence. So I already see like applications of CFD plus artificial intelligence. So using things more database inside of equation-based models, that's also a trend. And for operation of assets, for instance, for floating wind, any kind of things, ships, any kind of offshore, we see a lot of focus on digital twin. And digital twin is not more than to have a model remotely, so more than onshore of a structure that is offshore, where we can have a fast model. That's why the medium fidelity are needed to and together with sensors that are in real life, that are offshore, that's sending the data, and we're using artificial intelligence, we can improve these models and even predict what's going to happen to these assets in full scale some days before it happens, before some failure happens, before something happens hydrodynamically. And that's what people are working. We are also going towards that in small steps. Of course, we're a small company, we have a small institute, we have to work together with a lot of other people. But we need all these things. You just don't pick up a CNN and do a digital twin. You don't go to the shore, to offshore, and you put sensors. No, you need also models. You need also to understand. You need also some equations. I'm sorry, it cannot be only with data. So, and the last slide, what are our plans? Well, we would like to strengthen the cooperation links. You have seen some slides where we have done things together with other people, or open new ones, and for that open call to the audience. If you think that you can help us somewhere, or we can help you, let's talk one of these days. My email is everywhere, I think, in the call or in the invitation. And in terms of research, we'll continue with our line of open source tools, and we are very fond of that, but also by Fidelity. We're going towards a little bit of coupling, maybe weather forecast with CFD, and a lot of focus on satellite processing, getting more data remotely, like with the buoys and with the hydrophones to get data in order, or with the cameras to get data to train, and not only do web scraping, but to go really remotely. So maybe also satellites, to get satellite in order to be training and to be training the models. And maybe we would like to help you guys with something with our capabilities, but for sure also you can help us a lot. So still a way to go, but we are on our way to the fourth industrial revolution, and I thank you very much for your attention.